I think this we can like remove this this like no, then it's that's better. I think this now it looks okay, I think. Oh, we missed the mechanical torque, right? So rated mechanical torque, so we have 22 kilowatt, that's the rated power output, and then you have divided by the rated speed. So question 1, T out, that's the output power divided by the rated rotor speed. So this is 22,000 divided by 2,940. This is in revolutions per minute. So we need to do the conversion from revolutions per minute to radians per second. So which is 77.4145, let's say 46. Sorry, 71, right? 71.46. So then we were working with the fifth part, the resistance. So this is the third one. Sorry, second part, right? Second one. And the fifth one, we were looking at the rotor resistance, stator referred rotor resistance. We wrote down 455.1. This is the copper losses divided by 3 times I squared. So I we calculated that as 22.61, right? So 22.61 squared. So this turns out to be 0.2967 ohm. So part B is on the characterization, lock rotor test and the short circuit test. So says a no load test and a lock rotor test has been performed and the following results have been obtained. No load test, you're feeding the machine with 660 volts and the line current is 2 amperes and the power input is measured to be this. Lock rotor test, the line-to-line voltage is given, the current is given, and the input power is given. Second, so it says assume that the rotational losses scale linearly with speed and the no load speed is approximately at synchronous speed. Calculate the values of the equivalent circuit elements. Assume that the magnetizing branch is negligible during the locked rotor test. So if we look at the first part, we are going to calculate the lock rotor test, so lock rotor condition. So part B. So if we look at the lock rotor condition, we have let's say this circuit and then this. So under the lock rotor condition, the main current is through this path, and this is very small compared with the actual condition. So this current is really small. Therefore, we neglect this branch for this lock rotor condition. And then, so the current is given as 23.8 amperes. And then you are feeding in a voltage of line-to-line voltage of 274. So this is like star connected. So this voltage, this is the per phase voltage. So this is actually this divided by √3. This is a per phase equivalent. So the under lock rotor conditions, the slip is 1. So this resistance is 0. 0 means it's like a short circuit. It's equivalent to the short circuit test of the transformer. So we don't need to, this resistance R2 prime 1 minus S over S is going to be 0 since S is 1. So the total power consumed by the circuit is due to this particular element. That's the real power consumed in the circuit. And the total reactive power is due to this particular element here. So we can calculate the real power input. Let's say P lock rotor will be I squared, say I lock rotor condition squared. This R equivalent. So this includes the R1 plus R2 prime, the total combined resistance of the stator and the rotor, which is referred to the stator. Since we are dealing with a 3-phase machine, you need to consider like 3 times this, 3 times 3 phases. And this value is given as 1538. That's the power, 3-phase power. And this current is 23.8. And then we can find the REQ. So REQ will be 1538 divided by 3 times 23.8 squared, which turns out to be 0.9 or 5. And then the reactive power is associated with this particular element. So we can find the apparent power as lock rotor is the voltage times current, but then it's a we are given the line-to-line voltage. So we can write this as √3 V line-to-line, I line. That's the total apparent power. And then we have √3 times line-to-line voltage of 274 times 23.8. And you have 11295 volt ampere. That's the apparent power. So I'll probably have to correct this number here. So it's, and then, so Q lock rotor, that's the reactive power consumed during the lock rotor test. That's the apparent power squared minus P lock rotor squared square root. Oh. So this is the reactive power. And similarly, similar to this one, we can write Q lock rotor equals 3 times I lock rotor squared XEQ. XEQ is the element here, which includes the leakage reactances of the stator and the rotor. So we can write this Q lock rotor is equal 3 times I lock rotor squared XEQ. And then XEQ will be Q lock rotor divided by the current 3 times that. So that will be 11189.8 divided by 3 times 23.8 squared. So that turns out to be 6.8, sorry, 584.9. So that's the total reactances. So one of the mistakes that we've seen is that you kind of mess up the equations in terms of per phase power and the if you are given the total power here. So let's say in this example you are given the total real power, but then when you are calculating you need to have the 3 times this, otherwise you'll have a √3 times difference in the resistance. So that's the one of the mistakes. And then the apparent power, you always forget the √3 here, or you put 3 times that as well, and then that's one of the other mistakes you can do. So mind the √3s and the 3 times this here. Sometimes you might be given the per phase power measurement value. So then you need to multiply that value by 3 or just get rid of these 3 in the equation. So you need to understand what's being measured and how it applies to the circuit as well. So then this is the lock rotor test, and the other one is the no load test. So the no load test, it's running under no load. So that means the shaft is rotating. It's not connected to anything. So this the power output is 0. So you have this circuit. So if you look at the power input, we have a power input of 742 watt. So the total power in is 742 watt. But then if it's running under no load, that means the P out is 0. But then you also have the rotational losses. In order to run it at 0 speed, the motor has to compensate the rotational losses. It needs to overcome the rotational losses. That means PEM minus the P rotational losses is 0. That's this one. So rotational losses is given as 300 watt. So it says we don't we can scale it linearly with speed. So this, although it's 300 watt at 2940, if you were to scale it linearly with speed at 3000 RPM, so when it's running under no load, the speed is really close to 3000. Maybe it might be 2999 or something like that. So we can say under no load conditions, let's say no load rotational losses will be 300. This is at 2940, and then you scale it up a little, and you'll get this slightly higher value, which is 304. So we have 304.05 watt. So it's close, but there's a 4 watt increase if you increase it by another 60 RPM. This is the no load rotational losses. So if you look at the power consumed in this circuit, the current in this branch is really small, so we can neglect the power losses in this element. But the power losses in this element is this value. Not losses, it's the power being transferred to the mechanical domain. That's the this value here. So PEM equals P rotational losses at no load conditions. So here PEM is equal to P rotational losses, which is 304.05 watt. So we need to subtract this from the input power. That gives you roughly the power losses in this shunt core loss resistance. So P, let's say core losses will be 742 minus 304.05. Which is 437.95 watt. That's the core losses. That corresponds to the this particular resistance here. So we are given that this is running at rated line conditions. So we have a voltage of 660 over root 3 applied here, and the line current is given as 2 amperes. So we can write for this no load core losses, P core losses, we can write that as the voltage here, the per phase voltage squared divided by this resistance, which is, let's say, R0, but then mind that if you're looking at the total 3-phase power, you'll have 3 times this quantity. So if it's a star connected, like this condition, if it's star connected, this will be the voltage you apply here, which will be the per phase voltage. But then if you were to connect it in delta, then this voltage will be the line-to-line voltage. That's, you have 660 across these two terminals if you were to connect it in delta. So mind that as well, whether it's star connected or delta connected. The value here will be 3 times. It's always good to just have 3 times the terminal voltage, this voltage across one phase winding. So this, you mean, if you are given the power, right? Yeah. Yeah, you can divide it by 3 and then consider that to be just this bit here, then this goes down here. So we are calculating this value here. So if it's star connected, you can also simplify this to be like, let's say root 3 times V squared over R naught, and then you can write this as just V line to line squared over R naught as well. This is the term within this bracket is just the line to line voltage. But then mind, if it's delta connected, you'll have 3 times this, because it's the line to line voltage that you put in here, not, it doesn't simplify that. Yeah. So then R naught will be V line to line divided by P, call losses, which is 660 squared divided by 437.95. So we have, so the reactive power is due to this magnetizing reactance. So if we were to calculate that, you have the apparent power, let's say no load, apparent power will be root 3 times line to line voltage times line current, or you can do like 3 times this and this. Let's say 3 times 660 over root 3 times 2 gives you the apparent power. Which is 286.3 volt ampere. That's the apparent power. And then from that, we can calculate Q no load. That's apparent power minus the real power input. So that will be 22686.3 squared minus 742 squared square root gives you 2162.55 volt ampere reactive. And then similar calculation, you can find the reactance. So X, the magnetizing reactance will be V line to line squared over Q no load. Same concept as the resistance, voltage squared divided by reactance. So here again 660 squared divided by 2162.55, which is 201.42 ohm. So second part of that, to calculate the stator resistance with the use of the earlier calculated value of stator referred rotor resistance. So we calculated the stator referred rotor resistance as 2.967. That's R2 prime. So we found that, let's say R2 prime 0.2967, and then the sum of R1 and R2 prime, that's REQ, we found that to be the value previously calculated, which was 0.9050. So this was the REQ. So then we can find the stator resistance with this R1 equals REQ minus R2 prime, which is 0.9050 minus 0.2967. Which is 0.6083. Any questions on that? No questions? All right. So moving on to part C. So part C, it says calculation of operation under different test conditions. So the motor is supplied with a line voltage of 500 volts at 50 hertz and runs under no load. Calculate the line current and real power measurement that would be obtained under this condition. So this is like now you've reduced the voltage but kept the frequency the same. So all the reactance values are the same, but the voltage dropped now. So part C. So now we work with the values we have. So now you are feeding here 500 volts, which is 500 over root 3, and then we figured out these values. This we found that to be so this is 994.6, and then this reactance we found that to be X naught is 201.242 ohm. This is the reactance. And R1 and R2, this is we found that to be 0.9050, and X2 we found that to be 6.5849 reactance, and this is 0.2 967 1 minus S over S. So now it's running under no load. Still, our assumption remains the same. We assume it's close to the synchronous speed. So the power loss, the power you need to have is the same as before. In this element, we assume we need 304.05 watt to run it close to synchronous speed. So the power consumed in this is 304.05 watt. But then your core losses will change. So your core loss is basically this voltage over this value. So under the total power loss, let's say P measured, or let's say P in, will be this power plus the power losses in this core loss resistance. So you have this particular value. We neglect the power losses in this one because the current in that branch is really small, and this is fairly large. Plus, we have V squared over R here. So then we can write that as 3 times 500 over root 3 squared divided by 994.6. So here we have 251.35 watt plus the no load rotational losses. That's the amount of power that you have to feed into the motor. Which is 555.4 watt. So there are some inaccuracies with the answer I get here and the answer given in the sheet. So some where maybe there are some decimal place issues. Probably when you work through it, if you keep the decimal place number high, you'll get a more accurate answer, I guess. So we need to find the line current and the real power measurement. So then to find line current, we need to find the apparent power. So then we need to find the reactive power and then combine it with the real power. So Q in will be, so there's no reactive power in this branch. The current in this branch is really small. We neglect the reactive power in this as well. So Q in will be 3 times 500 over root 3 squared divided by 201.42. That's your reactive power input. Which is 1241.18 volt ampere reactive. So now we have the real power, we have the reactive power. So we can find the apparent power input. S in will be P squared plus Q squared square root. So that will be 555.4 squared plus 1241.18 squared, square root of that. Which is 1359.78 volt ampere. That's the apparent power input. So now you have apparent power, you have the voltage, so then you can calculate the line current. This is the line current I. So this, let's say S in, we can write that as √3 times the line-to-line voltage I line for a star-connected system. So then I line will be S in divided by √3 V line to line. So that's 1359.78 divided by √3, and the line voltage is now 500.
How would the F change if it was delta connected?
Yeah, so if it was delta connected, so then this will be the branch current. I will be the branch current. Then you'll need 3 times V line to line I branch current. Yeah. Otherwise, you need to have. Then let's say if you were to connect it in delta, then it'll have something like this. So here the I term here would correspond. This I term will correspond to the branch current here I. And then this will be your line current. And then you'll need to write this as S in equals 3 times this, let's say, branch current, V line to line I, or you can write this as √3 times V line I line as well. So in the star connected case, I line and the branch currents are the same, so it's just the same connection. Yeah. So we have 1.57-ish. Yeah, so that's when it's connected 500 volts and frequency is 50 hertz. Any questions? All right. So moving on to the second one, says the rotor is locked and a line voltage of 240 volts is applied. Calculate the line current and the real power measurement that would be obtained under this condition. So now the rotor is locked, so that means majority of the current flows through this path. This becomes 0. It's now like a lock rotor condition, and this resistance is 0 now. So we have 240 volts line to line, so that will be 240 over √3, and this. So in this case, we neglect the shunt branch. So we assume that the shunt branch doesn't produce much, doesn't consume much power. So since this is like R2 prime 1 minus S over S, under lock rotor conditions, S equals 1. So then that becomes 0. So one of the issues in induction machines is that compared with transformers, these elements are fairly low value. So if you look at transformers, the value of these are really high and these are really small, but then in this case it's fairly large. So most of these cases for large induction machines, you can assume this path is negligible. But then for really, the smaller the induction machine gets, these values become smaller, and then they are comparable to these values as well. So then you can't sometimes assume that these values are negligible sometimes. So you can actually neglect this. So you already have these values in your information. You already have the values. You've done the lock rotor test and the short circuit test. So you can see how big a difference it makes if you make the assumption that you neglect these or not neglect it. So let's say if you were not to neglect it, then let's say here you have this, and then you are feeding this voltage. You can calculate the total real power that then you'll need to factor in this in as well. So here it says you are applying 240 volts. 240 volts. So you have inductor, resistor, and a series resistor and inductor in parallel with that as well. So then you can find the power loss in this branch. Let's say this will be 0.9050, and this is J 6.5849. And then if you were to connect 240 over root 3 across this branch, the current in here, let's say I1 will be, let's say 240 over root 3 divided by 0.9050 plus J 6.5849. So that will be your current in this particular branch. So we can calculate that. So we have 20.84 and minus 82.17 amperes. That's in this main branch. You can also find the current in this magnetizing branch as well if you want. Say I naught. So I naught will be the sum of the current through the resistive element and the reactive element. So here we have 994.6 ohm. So the current in the resistive element will be 240 over root 3 divided by 994.6, and this is like phase angle 0. This is the current through the resistive element, plus the current through the inductive element will be 240 over root 3 divided by, here it's J 201.42. So this will be J 201.42. So if you resolve this, you'll get the total current into the magnetizing branch. Which is 0.139 0 plus So magnetizing branch current is like 0.7018 and minus 78.57. So compared with this 20.87, you probably can neglect this. It'll make like roughly about 4% error in the current. Yeah, so most of the time in the exam, we give like assume that for a short circuit condition, neglect this particular branch, and then for a short open circuit condition, neglect this part here. So that's pretty much standard in the exam. I mean, we are not going to twist it and then like ask like a twisted question. So if we were to consider both these, then we have to add this the current at this point. So let's say I line current will be this current plus the magnetizing current. So 20.84 minus 82.17 plus 0.7018 minus 78.57 gives you like 21.54 minus 82. This will be the line current, and then to find real and reactive power, you can do like a complex power. Let's say complex power will be √3 times V line to line, I line conjugate. So this will be √3 times 240 times 21.54, and the conjugate of this current will be phase angle 82. So you lose the minus there when you convert it to conjugate. So then the real value will be 10246.1 plus the reactive power will be 8866.8. So that's the real power and reactive power. And we need to find real power and the line current. So this will be the real power measurement. And this will be the line current. This magnitude will be the line current. If you were to neglect the shunt branch, your answer would be this, but then you can see the difference. There's a roughly about 4% to 5% error in if you make the assumption that this is negligible. But then if you don't have this information, you can't do anything. You have to neglect that anyway. And then finally in that part, you need to calculate the torque produced by the motor under the above lock rotor condition. So in this condition, we need to find the torque. So if you look at the PEM, we write this as 3 times R2 prime 1 minus S over S I1 squared. That's the electromechanical power. And the electromechanical torque 3 times R2 prime 1 minus S I1 squared over S divided by rotor speed. That's the torque equation. But then under lock rotor conditions, it's 0 speed. So this is 0. So then you can't use this equation here. It's going to be S is going to be 1, and then this is going to be 0, and this is going to be 0. So it's like 0 divided by 0. So we can find the limits of this. Let's say if S goes to 1, that means omega r goes to 0. Then we can write this as 3 times r2 prime 1 minus s I 1 squared over s divided by, we write this in terms of synchronous speed. So that's 1 minus s omega s. So we find that there's a common term there which causes that 0. So we can cancel that off. And then the torque becomes 3 times r2 prime I1 prime over s times omega s. So this here you can substitute under lock rotor conditions, s equals 1. So then there's some value there. So if we substitute the values, we'll have 3 times 2967 times I1. So now we are interested in this, the current in this branch, I1, that's the torque producing current. That's 20.84. Divided by slip is 1, it's lock rotor. So 1 times synchronous speed, so it's 50 hertz. And synchronous speed is going to be 3000 RPM. So we convert this to radians per second as well. So that's 2 pi over 60. That's the synchronous speed. So mind that you can't use this, you can't put just synchronous speed here. If it's, you need to mind the slip here as well. So this is only for the lock rotor condition. We put S equals 1. Otherwise, if it's running under load, then this will not be 1. Yeah. So which is 1.23 Newton meter. Any questions on that? Right. So moving on to part D. So calculation under different operating conditions and estimation of efficiency. So the motor is supplied at rated terminal voltage and delivers power at a rated speed of 2940. Verify the power factor and efficiency given in the nameplate data using the equivalent circuit calculations. So you are given some efficiency and power factor information here. So under rated conditions, it says you'll achieve an efficiency of 91.2 and a power factor of 0.89. So using this equivalent circuit, we should be able to estimate some information fairly close to those values. So if you look at the let's say power factor, say part D. So again the same circuit. So this is now running at rated conditions. So the rated voltage here, which is 660 over root 3, and then 994.6, and then this is J201.42, and this is 0.905, this is J6.5849. This is R2 prime 1 minus S over S. So So this is delivering 22 kilowatt. So this is producing 22 kilowatt. So we need to find how much power you are feeding into this circuit. So that includes, 22 plus another 300 watt as well, right? So that's the rotational losses. This is the PEM. So we need to find how much power you are feeding in, real power, and how much reactive power, and then find apparent power, and then the ratio between real power and apparent power will give you the power factor. So here, initially we assumed that the current here is 23.8. So here it's 23.8, and then we found the other current as 22.61, right? Here, that's the like 95% of this particular current. We assume that's in this branch. So these are all phasor quantities. So from this information, we can figure out the power, let's say P in. That includes the electromechanical power, PEM, plus the rotational losses, and the rotor copper losses, and the stator copper losses, plus the core losses. Oh no, sorry, this is our output power, right? This is the output power, P output power plus the rotational losses. This bit here is the PEM actually. So we have this value. We found that that's 22,300. We can find this. That's I squared R. And this is V squared over R naught. So here, let's say this is 22,300. That's the electromechanical power under rated conditions. That includes the rotational losses and the output power that you are delivering. Plus the whole thing here will be let's say 3 times I squared over R, 3 times I squared R. So I is 22.61 squared, and R equivalent, that's, we found that as 0.905. So that's 0.905. So this whole thing includes the rotor copper losses and the stator copper losses. And the core losses is 600 so I'll write this as V line to line squared over R naught. It includes like 3 times V phase voltage squared R naught. So that will be 660 squared divided by 994.6. That's the total power input into the motor, real power input. So then the total power input will be 22,300 plus 137.9 plus 437.96. We have 24,125.86 watt. So this is the total real power input into the motor. Yeah. That's from the short circuit test. Lock rotor test, right? Yeah. It's this one. Yep. So we can find the efficiency. That's the ratio between output power and input power. So that's P out over P in. P out is 22,000, and then you are putting in 24,125.86. That will be the efficiency as a percentage. So we'll have 91.18% estimated based on this equivalent circuit values. And then we need to find the power factor as well. So to do that, we need to find the reactive power. So the reactive power includes the reactive power of these two elements, the magnetizing reactance and the leakage reactance. So Q in will be Q leakage plus the Q magnetizing. So the leakage part will be I squared x naught, so that will be 3 times 22.61 squared the leakage reactance, which is 6.5, That's here you'll have 6.5849, that's the leakage reactance. That's the value here. And then the magnetizing reactance will be V line to line squared over X magnetizing reactance, which is 201.42. So that's 660 squared 201.42. That's the value from here, this value. So I didn't put the 3 divided by root 3 thing, so this will be just line to line, right? Yeah. So then you have reactive power. Um, 12261.48. So that's the total reactive power. So now you have real power input, reactive power input, so we can find the apparent power input. So S is P squared Q squared square root, so that will be this. Which is 27,062.9 volt ampere. So that's the apparent power. So the ratio between real power and apparent power will give you power factor. So power factor is going to be P in divided by S in. So that's 24125.86 over 27062.9, which is roughly 0.89, and that's what the nameplate says as well. So then it's close enough. So since we are running out of time, I'll probably skip the second one. So I'll upload the answers to the canvas. The second part, pretty much you need to reduce the voltage and put in the slip value. So it'll be pretty much the similar calculation to the tutorial 1, 2, 3 questions. So different voltage, given the slip, you need to calculate the current and the current and the phase angle of the current. And I'll move on to part E. If you have any questions on part D, you can ask me on Friday. Yes. Yep. Or you can ask me on Thursday. That special yeah.
That's a practice tip.
Yes. Yeah. Part E. So that's on starting of induction machines. So starting of an induction motor, starting torque, pull-out torque, variable speed operation. Calculate the overcurrent percentage during direct online starting of an induction motor. So that means direct online means it's you are just turning it on without any protection. So then you're under that condition, you have a lock rotor condition. At starting point, the shaft is not moving. The slip is 1. Then this is effectively a short circuit, and then the supply sees only these 2 impedances. So it's really a high current condition. So we need to find how much is the starting current compared with the rated current. So effectively you'll have, so part E, you have these 2 elements, and then 660 over root 3. This is a short circuit here under starting conditions. So this one is 0.905. This is J 6.5849. I think we calculated the current right here. So that's effectively the lock rotor test. No. So it's a reduced voltage. So here, the current here, I1, I1 will be 660 over root 3 divided by 0.905 plus J 6.5849. This is the starting current for that branch. turns out to be 57.3 minus 82. And the magnetizing branch, I naught, I naught is just the currents on these two branches. So that's 660 over root 3 divided by the resistance, which we calculated as 994.6 plus 660 over root 3 divided by J 201.42. Which is 0.383 plus 1.8918 minus 90. So if you sum everything up together, you'll find the line current, starting line current, I line will be the sum of this, and this together. So that will be 59.22 minus 82.05. So compared with the rated value, which is 23.8, we can find what percentage this is. Let's say percentage increase, so that will be 59.22 divided by rated current, which is 23.8 as a percentage. The current magnitude will be 248%. So it's like 2.48 times higher than the rated value. So that this is important in order to size the circuit breaker. Let's say overcurrent protection, it has to, when you turn it on, if it trips, then